Hello everyone, in this video we'll look at electric potential energy, for which we'll use the letter U, and electric potential, for which we will use the letter V. So these are two different quantities in physics that give us a clear definition of the properties of an electric field, the electric potential energy U and the electric potential at a point. So suppose we have a charge of plus Q placed in placed at a point in space. So this is our charge plus Q. As we already know that if we place a charge plus Q in space, it will create an electric field around itself. And so because of the electric field it creates, it is able to attract or repel other charges that are brought close to it or that are brought in its electric field. So suppose we bring another charge, a test charge Q0, from infinity to an arbitrary point. Let's say we bring a test charge Q0 from infinity to a certain point Q0, to a certain point P. So the charge we bring, the test charge is Q0. Let's suppose it is also a positive charge. This charge, the test charge Q0, is being brought from infinity. Now this is some kind of exaggeration. Of course, infinity means anything that is outside the electric field of Q is considered to be infinity. So suppose we bring this charge plus Q. Obviously, because plus Q0, obviously because this charge is positive, the charge that is creating the field and the test charge that we are bringing from infinity, there is going to be a force of repulsion. So there's going to be an electrostatic force of repulsion. In that case, let's call that force Fe. This is the force due to the electric field, so the electrostatic force of repulsion. And so we have to do work against the electric field created by Q in order to bring this charge Q0 from infinity to place it at this point P in an electric field. We have to do some work, and in doing that work we have to apply some force. Let's call that Fa. So in this, I mean Fe is the electrostatic force between the two charges, while Fa is the applied force, so the force that we are applying in order to bring the test charge Q0 from infinity to this point. Now, of course, since there is repulsion, we have to do work against the field. So let's calculate the work we have to do in order to bring the test charge and place it there. So the work done to bring the test charge, Q0 to the point P, well, it's difficult to calculate that work, but there's a simpler trick using calculus to calculate this work. So let's consider moving the charge Q0 through a very small distance. Let's suppose we could move this test charge Q0 through a small distance dr. So we can calculate the work done to move the test charge Q0 through a small distance dr. So let's call that small amount of work dw. So that's going to be equal to, so before we do that, we know from the laws of basic physics that work done, or work in physics, is actually the same as force times displacement. Force times displacement. So the small amount of work we have to do, let's call that dw, is going to be the force. So the force we are putting in is the applied force times the displacement. In our case, the displacement is dr. Okay, let's see what that gives us. Now this is only the work done in moving the charge through a small distance dr. Let's suppose we want to find the total work done. So let's find another color here. So let's find the total work that we have to do to move the charge from infinity to this point. So the total work W is obviously going to be the integral of all the small elements of work that have to be done. So this is of course a known law in mathematics. Integration means adding up very small tiny elements. So the work done, the total work, is going to be the integral from infinity, okay, the integral from infinity to r, integrating the electrostatic force, that's the electrostatic force dr. Okay, just something here very important, that as you notice in this diagram, Fe, the electrostatic force, and the applied force are actually in opposite directions. So we can conclude that the applied force is actually equal but opposite to the electrostatic force. So in this case, I could also say the amount of work done is negative Fe dot dr. Okay, notice that this is negative because the electrostatic force does negative work while it's opposing. So our total work done here is going to be the negative of Fe. So if I integrate this, we'll have negative Fe. Okay, choose this again, negative Fe dr. There we go. Let's substitute for the electrostatic force. We know that the electrostatic force, according to Coulomb's law, is going to be Q times Q naught. These charges are placed in free space, so we have 4 pi epsilon naught r squared. Also, just forgot to mention that the point P is actually at a distance r, so that's reasonable. Let us substitute for Fe. So our work done is going to be negative integral of Q naught over 4 pi epsilon naught r squared dr. Okay, there we go. And if you do the math here, you'll actually have all these are constants, so we have negative Q naught. Okay, this is from infinity to point P, which is at a distance r. This is over 4 pi epsilon naught integral of 1 over r squared dr, which gives us, okay, let's see, negative Q naught over 4 pi epsilon. So if we integrate 1 over r squared, we actually have negative 1 over r, which is integrated from from infinity to r. So we have infinity and we have r there. Okay, let's proceed and see what that gives us. Okay, so we have our work done is going to be negative Q naught over 4 pi epsilon naught. Let's substitute in the upper limit. It's going to be negative 1 over r, okay, minus negative 1 over infinity. So we know that 1 over infinity is actually 0. So we have negative 1 over r times this negative here. So we'll have Q naught divided by 4 pi epsilon naught r. So this work done to move a test charge Q naught from infinity to a point P in an electric field of Q is what we call the electric potential energy. So we conclude that the electric potential energy U is actually given by Q naught over 4 pi epsilon naught r. So this is the electric potential energy. It's a scalar quantity since this is just the work done to bring Q naught from infinity to a point P, which is at a distance r from the charge Q. So this is the electric potential energy that we need to do in order to bring Q naught from infinity to a point P. Let's go ahead and look at electric potential V, which is very different from electric potential energy. So electric potential. Now in physics, for purposes of generalization, let's just write that for easy generalization, so for easy generalization, it is always necessary to find find the potential. Now, every time we talk about potential, we actually mean the work done per unit measure. Okay, just like we talk about electric field intensity as the electric force per unit charge, also the electric potential is like the work done per unit charge. So in this case, the potential of a force is the work done per unit measure, and in this case our measure is going to be the unit charge. So we have already discussed that the electric potential energy is given by Q naught over 4 pi epsilon naught R. So suppose our test charge Q naught is actually a charge of +1 coulombs. So that means our electric potential, so if we have our test charge Q naught as 1 coulomb plus 1 coulomb in this special case, so this is a special case where Q naught is +1 coulomb, and in that special case the electric potential energy U is actually equal to electric potential, which we denote with letter V. So I now write out the formula for electric potential V as the, okay, if I substitute Q naught as +1 coulomb here, so I remain with Q divided by 4 pi epsilon naught R. This formula here gives us the electric potential of a field. Very important, the electric potential. So just to give you a clear view of why this is very important in physics, we know that the work done, which is also the electric potential, is given by Q naught divided by 4 pi epsilon naught R. I could write this same thing as you notice, this Q over 4 pi epsilon naught R is actually the electric potential V times the test charge Q naught. So would conclude that the work done by the electrostatic field is given by the potential of that field times the test charge Q naught. That means every time we know the potential of the field, we can easily calculate the work done to bring any test charge Q naught in that field without having to go through all the calculation, because the electric potential is a general property of the field. So the electric potential is a scalar quantity, and the units of V, the electric potential, so units of electric potential, as you notice from here, it's going to be the work done divided by charge. So the units of potential are going to be joules per coulomb. The units of potential are going to be joules per coulomb. Yes, so this is what we have as the electric potential, a general property of the field, and it's a scalar quantity. So suppose we have several charges. Let's look at the superposition of electric potentials. The superposition, okay, spell that right, superposition of electric potential. Superposition of electric potential. So suppose we have several charges. Suppose we have a configuration. Suppose we have a configuration of many charges in space. So let's say we have Q1, Q2, Q3, and so on. Perhaps also we have Qn, several charges placed in space. Let's have what that would look like. So have a charge Q1, have a charge Q2, have Q3, have Q4, and many other charges up to Qn. Suppose we want to find the electric potential at P. Suppose we want to find the electric potential at P. As you notice, there are several charges in this vicinity, in this space, all of them have electric fields around themselves, so all of them have an influence on the electric potential at this point P. So according to the law of superposition of electric potentials, the total potential or the electric potential at P is going to be, if we call that potential to be V, it's going to be V1 plus V2 plus all the other potentials up to Vn. Since potential is a scalar quantity, this holds and it is true. So every time we're calculating the electric potential, there is no need to change the signs of the electric potential. As you notice in the, okay, let's go to the previous, okay, every time you're calculating the electric potential of a negative charge, it will be a negative potential. If you're calculating the electric potential of a positive charge, it will be a positive potential. So it is logical to have this. Since potential is a scalar quantity, if you have a configuration of positive and negative charges, so if you have more positives than negatives, then that will have an impact on the potential, and so like that. So we'll look at in some other video, we'll look at some examples where we calculate the resultant potential due to a certain configuration of charges, but we'll do that in a moment. For now, let's look at the potential difference due to a point charge. Very important phenomenon here. Potential difference. The potential difference, we usually denote that as PD, the potential difference due to a point charge. The potential difference due to a point charge. Every time we talk about a point charge, we actually mean a charge that is small compared to the distance on which we are measuring its potential. So that's why we say point charge, a very small charge compared to the distance where we're doing the calculations of potential and electric field intensity. So let's use a previous illustration. Suppose we have a charge plus Q placed in space. It creates an electric field around itself. We know already about that. So let's say at a certain point, let's say at a certain point P, we actually bring or we put there a charge of +1 coulombs, and we want to find the potential difference at 2 points. Let's say we have 2 points. Okay, we're going to take point A. Let's take point B here, and then we take point A here. Let's put some distances here. We have a distance from the test charge to A. Let's call that distance A. Let's call the distance from the charge, so it's not the test charge, it is the charge which is bringing out the potential. Let's call this distance B, and let's call this distance here R. It's not actually so necessary in this configuration, but there we go. So let's suppose we want to find the potential difference between points A and B. In other words, if I move a test charge from B to A, how much work will I have to do? What's the difference between the potential of this point and this point? Let's begin with an analogy. Let's say I have a stone and I raise it up to a certain height. Let's say this is a height h1. Okay, let's say this is a height h1, and let's say I increase the height to this point, and I call this height h2. So the potential energy at this point is going to be mg h1, and the potential energy at this point is going to be mg h2. So this is potential energy 2, this is potential energy 1. I can find the potential difference by subtracting the higher potential minus the lower potential. The same applies to electric fields. We can find the potential difference between 2 points. Now, of course, there are two approaches. There is a simple approach of simply subtracting the two potential differences. So I would say the potential difference, we commonly use PD. Let the potential difference between A and B, the potential difference between A and B, I'll call that VAB. So it's going to be the difference between the potential at A and the potential at B. Now, of course, since potential is given by Q over 4 pi epsilon naught R, as you can see, the potential at A is actually greater than the potential at B for this positive charge, because B is at a greater distance than A. Okay, let's clear up that, then we continue. So that's the potential difference between A and B. It's VA minus VB. So the potential at A is given by Q divided by 4 pi epsilon naught A, minus the potential at B is given by, okay, I think it's good to use the same letter Q here, Q over 4. This is the charge here, 4 pi epsilon naught R, not R, A. That's the potential at A. Then the potential at B is Q over 4 pi epsilon naught B. So the potential difference between A and B is actually Q over 4 pi epsilon naught. I pull out the common factor, then I have 1 over A minus 1 over B. That will give me the electric potential between the points A and B. Now, if you're preparing for an exam or something, they might want you to derive this in a slightly different way, which I will not use, but I'll show you the highlight. So suppose you move the test charge, the 1 coulomb charge, from point B to point P through a small distance, dr. Suppose you do that. Okay, just make this better. Suppose the distance between B and P is a small distance, dr. You would simply say that the potential difference is the same as, okay, this is just another way, the small amount of work done to move this charge from B through a small distance, dr, is going to be, okay, the product of the electric force, that should be a minus, because the electric force is acting, let's just use another color, the electric force is acting in this direction while the applied force is actually acting in this direction. So, and we know that FA is negative FE, so I should be using FA here, but I use negative FE times the distance, dr, and that would give us the total work done, which is also serving as the potential difference between A and B. If you would like, that would be the integral of negative Q over 4 pi epsilon naught R, that's from point A to point B. There we go, from point A to point B. And in this case, you would actually find what the answer is if you take on this integral. Okay, this is with respect to R. You'd actually get the same. You see, we are not including the test charge Q naught, because Q naught, the test charge, is a 1 coulomb charge, so that wouldn't be necessary in this case, since that's why even here we are putting potential, not work done, because potential is the work done when Q naught is 1 coulomb. So there we go. That would suffice for us to find the electric potential. That would be a good exercise to try out, and you would actually come up with this same answer, I believe. Okay, this is R squared. Yeah, that's R squared, because this is the electrostatic force. Okay, let us look at the relationship between electric field intensity and electric potential before we look at problems to the numerical problems to do with electric potential. So the relationship between electric potential V and electric field strength or electric field intensity E. So let's begin with an assumption here. Suppose, or let dx be a small distance, let dx be a small distance between 2 points A and B. Let dx be a small distance between 2 points A and B. So suppose we have a charge here and we have some 2 points along the line, this line here. We have some 2 points A and B, and there is a small distance dx between these 2 points. So suppose we have to move a unit charge from A to B. So suppose we have to move a unit charge. Unit charge means +1 coulomb from A to B. In that case, of course, we already know that the work done is going to be the force times the displacement, which in this case is dx. As in the previous explanation, the electric force acts in that direction while the applied force acts in this direction. So this is actually the applied force, which would actually be negative Fe dot dx. So that's a negative Fe. Okay, let's proceed. In this case, since the test charge is a 1 coulomb charge, dW, the work done, is going to be the electric potential. So we will not call that dW since the test charge, is +1 coulomb. So these things are very important to notice here. Because of the test charge being 1 coulomb, then the work done is going to be dV, the small change in potential. That's the same as the small work done. Also, the electric force is going to be equal to the electric field intensity, because the electric field intensity is the work done per unit positive charge. So that's reasonable. So I substitute all those here now, and I'll have this formula now becomes dV equals negative E dx. And so we'll conclude that E is going to be negative dV dx. In this equation, this gives us the relationship between potential, the electric field, and the electric potential. Also, the quantity dV dx is known as the potential gradient. This is known as the potential gradient. Okay, so why is the potential gradient negative? Well, it shows that the potential decreases in the direction of the field. So as we move away from the charge plus Q, the electric potential decreases as we go in the direction of the electric field. So this is a very important relationship that is applied in many calculations, as we'll see, or as you may study in more advanced courses. Okay, that's it for this video. Hope to see you again.